Hey, Vlad here, Dependencies.com. Welcome to another video. In the previous few videos, we kept stumbling on implicits left and right, and today we're going to put the homegrown collections library on pause for a bit and learn about the most useful applications of implicits called typeclasses. And whereas we used implicits so far to implement some fancy looking DSLs, typeclasses will bring your game to another level. So I hope you brought some popcorn. Let's do this. Alright, here's the deal. Typeclasses can be explained in a very simple way in only like 5 minutes, but as you know by now, I try to make my videos very fundamental, so we're gonna go the longer route. Typeclasses are a mechanism which is sometimes embedded straight into the language, or in Scala it is encoded with implicits, and it is a mechanism for adding behavior to already existing data structures which may or may not be yours. And they're most useful in statically typed languages because the so-called typeclass instances are being resolved at compile time. And so if your code compiles, then you have found the instance of the typeclass, and if it doesn't, then you haven't found it, so you know right away that something is missing. Our journey begins in the video that I made almost a year ago. It is the video about objects versus data structures, and it would be super awesome if you could open it in a different tab, watch it first, and then come back here. I'll wait. Welcome back. Oh, you didn't watch it? Okay, fine, let me sum it up. Object-oriented languages have this thing called subtype polymorphism, where a type can take in different forms, and then based on the form, the behavior of that type will be different. The canonical example for this would be a type called animal, and you would have two subtypes of it, cat and dog, and then you will have an algorithm which uses an animal and then it calls make noise on it, and then dependent on whether the animal is a cat or the dog, the behavior of make noise would be different because obviously cats and dogs make different noises. Subtype polymorphism is a type of so-called ad hoc polymorphism where the behavior changes based on the form of the type. This in contrast to parametric polymorphism, where the behavior does not change based on the difference of the type. For instance, the behavior of the method called size defined on list will remain the same independently whether you call it on a list of strings or list of characters or list of dogs or cats or animals. You get the idea. Now, a truly useful language would require both kinds of polymorphism, the ad hoc polymorphism, which embraces the differences of the form of the type, and the parametric polymorphism, which ignores the difference. As I already said, object-oriented languages implement ad hoc polymorphism with subtypes for their objects. But what do functional languages do? They don't even have objects, they don't even have subtypes, then what do they have? The answer is typeclasses, and over the course of the next few videos we're going to learn their ins and outs and realize that even though they were originally designed to add behavior to data structures, in a language like Scala or Java they can actually add behavior to objects as well without any additional cost. As always, we're in the Ubuntu virtual machine and we're using Sublime Text, the editor of my choosing, which is fully maximized so that it can save some space, and we're using a wonderful plugin called Terminus which emulates the entire terminal for us, which runs SBT, which we usually use to rerun the test every time we save the file. So what you see here is a project which is basically the recreation of what we had back in that other video. In that other video we had a library and we had an application, and the application had a source code dependency on the library. Now in this one we'll have three libraries. They have absolutely no dependencies between each other, and we still have the application which has a dependency on all of them. Now all of this is already set up, so I'm just gonna go through it file by file so that you see all the changes. So first of all, we're starting with the build properties in the project folder, and I don't want it to spawn over here. I want it to be over here. We're using SBT 0.13.6, even though SBT 1 something is already out. I'm using still 0.13.6 because I have been using it for quite a while in the homegrown collection series, and I just don't want it to change for now. Now in the build file, which is larger than usual, we have the common suspects, we have the version, which doesn't really matter, we have organization, which also doesn't really matter, it only matters when we publish stuff. We're using Scala version 2.12.4 for the same reason as the SBT version, because as of right now 2.12.8 is already out, and by the time you're watching this video maybe even Scala 2.13 is out. Now this line over here makes sure that every time we use continuous compilation or continuous testing or so on, and so on, that the screen of the terminal will be cleared first, so we see only the last iteration of the compilation or of the test. Now, these are the Scala compiler options that are necessary for implicits, because we're going to deal with implicits a lot today to encode type classes. These ones are just a bunch of aliases. For example, I can type an app over here and it will switch to the application projects, or I can type in A, it will switch to the library A, and so on. And I can type in root and it will jump back to the root of the multiple project. Now, these lines over here just make sure that we have this fancy prompt that you're seeing down here. Welcome to Typeclasses project, welcome to library A project, and so on. And we have 3 of these libraries, library A, B, C, and I called their folders like this because I really wanted to make sure that, because they're sorted by name in the folder over here. So yeah, as you can see, they have 0 dependencies between each other, but then we have application which has a dependency on all of them. And as of right now, we only have the code that is in library A. So this is what we had in the previous video. So I already split my windows with the plugin called Origami into A, B, and C. So I'm gonna open shape that you're seeing over here. This is the only code that we have in library A. Library B is empty, library C is empty so far. So let me show it to you. So this is exactly what we had in the other video. So we have the object-oriented version of the shape, which was one method called area, and we have the data structure or data-oriented version called shape DS, which stands for data structure, and we have a final case class circle and rectangle DS. Okay, and then in the application, which I will open over here, where we have the build file, where I actually don't really need it, I will open the object-oriented version of the main method, where we have the class circle OO. It extends shape OO, which is over here. It implements this area. It overrides a def with a val, which is a valid thing in Scala, which doesn't really matter for this video, but still. And we're doing the same thing with a rectangle. Then we're creating 2 instances over here. This is ad hoc polymorphism, subtype polymorphism, right? We're saying, hey, we want a shape, but we're giving it a circle just to play around. We're printing them out. We can actually run this thing. So if I go to application and I say run, we have 2 main methods, and I'm going to run the second one, which is the main OO, and something comes out, circle area, rectangle area. And the same thing is going to happen for the main for the data structure. So we're going to have, actually, let me scroll down over here. So we have the data structures over there. And I'm going to open the main data structures file. It is a very similar thing. So at the bottom, we're instantiating the circle and the rectangle. Again, this sort of looks like ad hoc polymorphism. This is sort of problematic in Scala because even though we're dealing with data structures, we're still using subtype polymorphism. We're still using the extends keyword, right? So circle extends shape, but we're using it in a different way. Like usually with subtype polymorphism, when you design your hierarchies, the top class should not know anything about the children, right? So it shouldn't know about the classes that extend itself. With data structures, it's different. Like this is an algebraic data type, so you have all the possible instances in this file. Okay, so yeah, but it sort of still looks like ad hoc polymorphism over here. It's a different form of the shape ds. Okay, so if we run that, we're going to see the same result, and it's happening because over here at the top we have an object called shape ds operations with a method called area. We just pattern match on the shape, and we're doing exactly the same code as in the object-oriented way, right? So if I go over here, for example, this is the radius of the circle, which I hope that I wrote down correctly this time. I made a mistake in the other video, and it's the same code over here basically. Now, the conversation in that other video was about, okay, what's going to happen if we add a new type? Or what's going to happen if we add a new behavior? How will the object-oriented solution react to it? And how will the data structure solution react to it? Today, we have an entirely different conversation. In fact, we're going to add types and behaviors. And also, we're going to up our game a little bit, and we're going to add them into completely separate libraries. This is why we have the library B and the library C. The library B is going to have other types. They will be similar to shapes, but they will not be shapes, but they will have the same behavior. So they will have area. In the library C, it will have algorithms that will want to deal with both the shape and the and this other entity that we'll create in just a second. In fact, let's go and create them right away. So I'm going to go to library B. Over here, I'm going to create a new file, and I'm going to save it right away into source main Scala library B, and I'm going to call it geoentity. Geoentity.scala. Now I wanted to open over here because this is the library B, and I'm going to collapse the sidebar because I'm literally running out of space here. So let's create some space over here, right? Over here as well. You know what? I'm going to copy this entire thing over here. I'm going to paste that over here, right? Because this is going to be very, very, very similar. Okay, so we're going to go up and we're going to start at the top with the type called, instead of shape OO, we're going to have geoentity And as I said, it will also have the area, okay? And then we'll also have over here where it says shape, I'm going to have geo entity ds, okay? And instead of circle ds, we're going to have continent over here, continent, and we're going to have country over here. And the country is just going to have the name, like that, name string, and the continent is going to have countries. We're going to have some fun. So it's sort of like a bit of recursive definition here. Countries, which is a set of country ds, like this. Okay, so let's see if we can save that. So I'm going to go back to root. I'm going to start compiling everything. All right, it looks like it's going. Come on, it's one file. All right, there we go. Next thing that we'll go to the main OO and over here. So I'm going to copy, for example, circle, right? And I'm going to go down under the print lines, and I'm going to insert it over here like this. And this is going to be our first object-oriented class. It's going to be continent, right? And continent only has, what did we have in the data structure? We said continent only has countries. All right, so I'm going to go and say countries like this, and which is a set of country, which we don't have yet. So we're going to have country OO like this, and it extends, not shape, it extends geoentity OO, right? But it still has an area, and the area is going to be, okay, let's just go through the countries, convert them to list, and map them to area, and sum them up. Very important, every time you're dealing with sets, convert them to list every time before you're calculating any sort of sum or any sort of mathematical calculation, because countries might be distinct, but as soon as you map them to area, their areas might not be distinct, and then you will lose some values, right, because of the duplicates. Okay, the other thing is going to be, let me copy that. In fact, let me save that first and see if I did mistakes. Okay, country OO doesn't exist obviously yet. Okay, so this is going to be country OO, and what it would say, it's going to have just a name, I believe. Yes, name string. Okay, and its area is going to be just 1337 because we're just playing around. Okay, like this, and now it should compile. It should be fine. All right. Now we're not going to create instances of this because this is very simple code. These days at this level, you should be able to understand how this is going. Because I want to save some time, because like in my head, I think this video is already going to get around an hour long. So I'm really trying to save time as much as I can. In fact, for the rest of the video, we won't even run any code. We just care about compilation, right? If it compiles or not. So we're going to go to main ds, and we have object shape ds operations, and similar to that, I'm going to copy that. And I'm going to go down, I'm trying to follow the same pattern. So I'm going to go under the print lines over here, and I'm going to paste that over here. So we have shape ds operations. Instead, we're going to have geoentity ds operations. We're going to have area as well, but now a geoentity will come in like this, geoentity, and the type is going to be over here, geoentity. We pattern match it on the same on it the same way. We have the country, which is a country ds, and the code to calculate the area is going to be the same. It's 1337, same way. And then if it's a continent, which is a continent ds, then the area is going to be the same as in the object-oriented version. So we're going to go to the continent, and we're going to go to the countries. I'm going to convert them to list, same way. We're going to map them to area, add expansion here, right? Recursive call to this area function. All right, and we're going to convert, not convert it, but we're going to calculate the sum, and otherwise it's going to be an unknown entity. And let's see if it compiles. It should. Sometimes when you see this array expansion mistakes, you actually have to look a bit closely. See, it says 2 errors. So if you scroll up, it will actually say that, that continent doesn't exist. So only because I made a typo over here, continent, now it's going to go away. See, there we go. All right, so let the fun begin. So what we want to do is we want to create a complicated algorithm. Now it's not going to be complicated because it's an educational video, but it's, we're going to call it complicated algorithms, right? So we're going to go down over here, and we're going to create an object called complicated algorithms. All right, not really complicated, but the point is that you know, they pretend to be complicated, and they should work with shapes and with geoentities, right? Because they work with areas. So this complicated algorithm will take something that has an area and it will calculate the area twice, right? So the way we do this is we're just going to say, okay, we're going to take a shape and we're calculating a double, right? And the whole complexity of the algorithm looks like this: shape.area times 2, right? But you know, we're pretending that this is a complicated algorithm. Now, how are we going to do this if we want to make it work with geoentities as well? Well, the first thing that we're going to try is we're going to try overloading, function overloading, right? So we're going to say, okay, instead of shape, we're going to take a geoentity. I'm going to call it geo from now on, right? So I can say geoentity OO and double, and the code, this is sort of the point, it will look the same, right? Area times 2. Area times 2, right? And the same thing would work for the data structure approach, right? So we're going to go down there to the main data structure over here. We're going to go paste it in. It's just that instead of getting shape dot area like this, we're going to go to shape ds operations, operations like this. We're going to say area. We're going to give it the shape, and obviously it's not OO, it's ds, right? So over here it's ds like this, right? And the same thing over here. Instead of calculating the area in this object-oriented notation, we're going to go to the geoentity ds operations, and we're going to say area, and we're going to pass it the geo object, and it should work exactly the same way. Now, the problem that we're trying to solve here is obviously to remove this duplication, because if we keep adding types independently of, you know, if we keep adding types in the OO version or in the data structure version, you know, this code is going to grow out of hand. Now, technically, in the data structure approach over here, right, we could actually make the type more flexible, right? So we could create one of them, and we can say that any comes in, right? And then you can pattern match on anything. But this is kind of ugly, and this is not what we're looking for. Function overloading accomplishes basically the same thing. It's just that it's a little bit more type safe. Okay, so instead of going with this any route, you know, we might as well use function overloading. And the next thing is that we need to realize that this complicated algorithm, it has a direct dependency on the shapes, right? Both on the OO version of shapes and on the data structure of shapes. So if you wanted to remove this dependency, we would need to do something like this. We would need to go and define a trait, something that has area, and it has an area, right? And then we would write this algorithm in such a way that it works with something that has area. So you could now go here and say, okay, this is something that has area, right, of type something that has area, and we just take it, something that has area dot area times 2, and we don't even need the second one, right? So we sort of, you know, we sort of remove the duplication, and we can do the same thing in the other version, in the main OO version, right? Over here we do that, and I'm going to copy paste the rest, right? Because it's literally the same. And in fact, because it is the same, see, it's the same solution for the object-oriented version and for the data structure version. Now, functional languages, you know, they don't have something like this, right? They can't define like a trait, and they can't have things that extend this because they don't have subtype polymorphism. So we're going to get to that a bit later. But you know, we're slowly moving towards type classes, and as I already mentioned in the previous, as I already mentioned in the beginning of the video, this approach works both for the data structures and for the objects, right? Which is kind of cool. So the next thing that we're going to do is we're going to notice that now we don't have the dependency on the exact shape and on the exact entity. And because also the solution works for both of them, we're going to take it out completely, and we're going to move it to the library C. So we're going to take that. I'm going to cut it out, right? Save. Also here, I'm just going to remove it. Okay, and I'm going to go over here, which is library C. I'm going to create a file. I'm going to save that as complicated algorithms, right? And I need to make sure that I go into library C. Okay, source main Scala. All right, okay, dot Scala, like that. There we go, and paste it. Right, so I pasted it. Let me create some more space so we see it. Okay, it's over there, and notice that this trait, it had to come along, right? So these algorithms now, their only dependency is this tiny thing. Now there's one thing that I sort of forgot to mention before I moved it. Imagine that I hadn't moved it yet, right? How will we actually adapt our shape or our geo entity to something that has area? Remember this trait, something that has area, it was down there in the application. The application had the dependency on the shape thing and on the geo entity thing, which reside in libraries A and B respectively, but not the other way around, right? So we can't just go to the shapes and say, okay, extend something that has area. We can't just go to the geo entities and say, hey, extend something that has area. And now it's in the library C, right? So we have 3 independent libraries maintained by completely different people, so we can't just go there and change their code. We're obviously not going to talk about open source here. All right, so these 3 libraries, they don't know anything about each other, and now we have an application where we throw in all of these 3 libraries, which is, by the way, a super common thing that is happening in production. In fact, this is the only thing that is happening. You have an application, you throw a bunch of dependencies in there and call it a day, right? So how do we adapt our application to all of these 3 libraries? How do we make them work with each other? And the solution goes by the name of the adapter pattern, which is one of the multiple patterns in the famous Gang of 4 book. Now we're only going to do this for the data structures to save some time, but I promise you that the solution for the object-oriented version is almost line by line the same, like 99% is the same. Okay, so the first thing that we're going to do is we're going to go to the main DS and we're going to create some more space. We actually don't need so much space over here. We're only caring about compilation. Let me save the file and see if we actually see everything that we care about. Yeah, we only care about success over here. Okay, so what we will do is we will create a class called shape adapter. Shape adapter, right? So it gets in the shape, right? And it gets in the shape data structure. Now the shape adapter now can extend something that has area. Now we couldn't do this before, right? We can't go directly to the shape and say that it extends something that has area because it's not in our control, it's not in our library, but we can do this with an adapter, right? So it's just a wrapper around the shape that extends something that has area, and all it does is it overrides the area over here, right? It says final override def area, which is a double, could also be a val, doesn't really matter, okay? Equals, now we're gonna go to the shape ts operations, right? Get the area out of shape. So it's basically just delegating to the shapes. That's all that a regular adapter would also do. You know, a regular adapter in the as an electricity outlet. Same thing, right? We just delegate the electricity to the actual device. Now, just as a convenience, we're also going to have a function that creates a shape adapter, right? So we're going to call it the same way. We call it shape adapter. It gets in the shape, which is a shape ts, and it returns something that has area. Okay, all it does is says new shape adapter with a shape, right? Just a convenience. So what we gain now is that we can go to the complicated algorithms, right? This one, I'm going to copy it, paste it over here, and now we're going to call area twice, right, which is this method over here. Now it wants something that has area, so we obviously can't give it a shape, right? We have a circle somewhere laying around. We can't just do that, right? So that doesn't compile. So what we're going to do is we're going to wrap that into a shape adapter, right? So we're calling this dap, which is called by capital camel case. You will see why I'm doing that a bit later, but that's essentially the pattern. This is the adapter pattern. You create adapters, you wrap your actual things in that adapter, your actual devices. I'm going with the electricity outlet metaphor here, right? And then you just pass them along and they just delegate all the calls to the actual device. Now, by the same token, you could go and define an adapter for the geo entities thing, but I'm not going to do that just to save some time. But essentially, you get the idea. Now, the adapter pattern is probably the most flexible pattern and the most useful pattern in the Gang of 4 book, if we don't count the dependency inversion, right? Because if we did, then the dependency inversion would be technically the most useful pattern in the book. Now, the adapter pattern and the bridge pattern are very similar patterns, and I'm going to say something about their difference by the end of the video. Their goal is to adapt 2 different families of algorithms to each other, right? So we have the shapes, we have the complicated algorithms. We adapt them to each other, right? We have the geo entities and the complicated algorithms. We adapt them to each other, right? That's the whole goal. There's only one problem with this pattern, and this is its size. So it's a bit bulky on the syntax, and I'm gonna show you in a second what I mean. Imagine that we had a class container, something like a list or option. So I'm going to go to main DS. As I said, we're going to do most of the things in the main DS thing. I'm going to go over here and I'm going to create a final case class container, right? So it's a container of some sort of element, right? And it just has an element, right? A simple data structure. Now, let's say that we wanted to do something like this. We wanted to pass in the container container of the circle. Right, so the shape adapter obviously doesn't do that, so we need some sort of container adapter, right? Container adapter, right? So we're gonna go and implement it, right? So we're gonna have a container of something that, you know what? I'm gonna copy both of these over here, right? Whoops, what did I press? Both of these here. Okay, so I'm gonna copy them and just paste them over here, and instead of shape adapter, I'm gonna call it container of something that has area, right? And now it has a container over here. The container is not a shape ds, the container is a container of something that has area. Okay, so I sort of jumped ahead a little bit, right? We're not going to implement the containers for you know, we're not going to have one container adapter for the shapes and one container adapter for the geo entities. We're going to go straight for the container of something that has area so that we can reuse this adapter for all the containers. All right, so the only thing that is left to do over here is to say that the area is not going to be retrieved like that. The area is going to be retrieved by simply going to the container, retrieving the element, and asking for the area. Okay, let's see if I did any mistakes. Okay, I did something wrong. Container adapter. Actually, this is not something wrong. This is exactly pretty much what I wanted to show you. No, hold on. I called it container adapter. Hold on. Container of something that has area. All right. Let's see. All right. So this is exactly the problem that I wanted to show you, is that it says that found a shape ds over here, right? But it requires something that has an area. Now, obviously, we could go in and manually convert this circle to a shape adapter, right? Like this, okay? And now this solves the issue, but this gets like way too bulky. This gets even more bulkier than what I wanted to show you. So the other solution would be to say, okay, so let's not create a container of something that has area. So let's not create this kind of adapter. Let's create a kind of adapter that just wants some t, right? It wants some t, not like the drink tea, right? It wants some t, right? So it says, okay, so this is going to be my container of t, right? And what it will also have is it will have a function called convert that will be able to take that t and convert it into something that has area, okay? Like this. So we have to do the same trick over here, t, okay? And we need to pass along this function, which is convert, right? We're going to have it over here as well. I'm going to go and paste that over there like that, okay? Maybe we can do like this and that so that it looks a bit more readable. I don't have scalar form, so I can do pretty much what I want. Okay, so yeah, that looks fine. Let's see. Okay, so now the last thing that is left to do is we actually need to use this convert function, right? So we need to convert the container element. Right, so basically the conversion is happening for us, so we don't need to do manually this thing. Okay, I think it's time that I start looking at the error messages. Okay, so new containers, keep pasting in the container. Okay, where is it? Over here. Yeah, I forgot to change that to the T. There we go. Okay, so there's only one error found, and this is the place where we were doing the conversion manually, right? So the whole point is that we don't need to do this manually. We're going to just pass in the circle, right? And we're also going to pass in the shape adapter, and then the add extension is going to kick in, and it's going to convert that into a function. What did I do wrong? Okay, container of circle and shape adapter. It says unspecified value parameter convert. Okay, this means that there is a parenthesis issue somewhere. Okay, so hold on. If I'm creating a container, oh, it should be called like this. What did I do there? Yeah, so the parenthesis issue is over here, like that. So it's the container of a circle, comma, the shape adapter. And let's see if I got the parentheses right this time. I did not. This one seems to be too much. I believe that should be fine now. Yeah, that should be fine. Okay, so these are all the parentheses. So let's go through this real quick. So we're going to the complicated algorithms, calling area twice, which wants something that has area. So we're giving it the container of something that has area, and this container of something that has area, it wants the container of some t, right, the container of circle, and it wants a function that can take a circle and convert it into something that has an area, which is the shape adapter. Shape adapter is doing exactly that, right? It's over there, right? It's taking a shape, converting it into something that has an area. So it's basically exactly like I explained. It's just a bunch of adapters stuck together. It's very, very bulky on the syntax. Now we're very super close to learning about type classes and see how adapters relate to them. Now, as I already mentioned in the beginning of the video, in Haskell, which is a language that, if not invented, that at least popularized type classes are a language level feature. And in Scala, we're going to use implicits to sort of mimic it, right? You know, the proper word would be to encode it. We're going to use implicits to encode type classes. Now, pay close attention to what I'm going to say next. There are two possible encodings of type classes in Scala, and both of them use implicits. Now, one of them sort of relies on the second one, and therefore at some point the entire community decided never to speak about it again, and you know, we'll pretend like there's only one encoding. Similarly to the cake pattern, you know, it's, you know, there was a time where everybody was happy with it. Now it is pretty much frowned upon, and you know, but I still made the video about it, so therefore I'm still gonna show you the first encoding. You cannot imagine how much hate I received for making this cake pattern video. Jesus Christ. This first encoding that I'm going to show you, it will actually be even deprecated soon. I believe in Scala 2.14, and then in Scala 2.15, or maybe it will become Scala 3. It will not even be present in the language anyway. So step one is we're going to go to the container of something that has area, right, to this case class. And we're going to query the parameters, right? So this is not going to be a parameter list with 2 parameters. This is going to be 2 parameter list with 1 parameter each. So this comma is going to be like that. So this parameter list ends. I'm going to press Ctrl J to join the line, right? And this is going to be the second parameter list. Okay, and now I'm going to go and press enter over here, right? So we have 1 parameter list, 1 parameter container. The other parameter list converts also only one parameter. And we're going to do the same thing in the class, which is technically not required, but we'll just do it anyway, just for the symmetry purposes. Okay, like that, and there's another brace over here, Control J, like that. All right, so this looks very, very similar now. And now at the point where we're calling it, let's see if it compiles. Okay, first of all, over here, we need to do it like that. Okay, and at the point where we're calling it, it should be it should look like this. Okay, so this is the first step. Now the next step is where implicits come in. All of these dapps that we have to, you know, that create the adapters, that will become implicit. So this one will become implicit, and this one will become implicit. And the last step would be is that this parameter, this entire parameter list, this convert parameter list, it will also become implicit, like this. Okay, so if we save that, everything should behave exactly the same way, but all of a sudden our code gets nicer. So if we go over here, right, because the shape adapter is implicit, we don't have to pass it explicitly, right? So we can, in fact, you know, I'm gonna duplicate the line, and also I'm gonna remove that, right? Okay, so we can just do circle like this. Okay, this is happening because the shape adapter is implicit, right? There was only one implicit required. And the next thing over here is that the shape adapter, this entire parameter list, is also not required. So if I go over here and I remove the shape adapter from here like this, then the compiler will find it, right? So it wants over here at this position a convert function which takes a t and produces a something that has an area. Now the type inference understands that the t is a circle, so it looks for a function that can take a circle and to convert it into something that has area, and this is a shape adapter because it's marked implicitly. Eta extension is going to kick in and convert it into a function object which takes a circle, converts it into something that has area. Now the third implicit that we used was this one, right? So the container of something that has area is also an implicit, right? So now we can actually go even further and we can remove this entire thing, right? So the same thing as was a transformation from here to here, this is the same transformation from here to here. So we don't need to explicitly call shape adapter, or in this case the container of something that has area like this, right? So we can just pass it the container of the circle. And this is, by the way, called implicit derivation. So we're calling container of circle, right, the compiler is going to try to find a function that takes a container of circle and converts it into something that has an area. Now it finds this one, but this one also has an implicit requirement, right? So it says, oh yeah, but I also need a function that takes a t and converts into something that has area. So the compiler knows that the t is a circle. It goes and starts to look for the shape adapter, right? So now, you know, with implicits, this code got, you know, pretty nifty and very much usable. So the compiler is doing pretty decent work for you here. So look, over here it uses one adapter, right? So it finds one adapter, and over here it actually finds two adapters, right? It finds the adapter, this one, and it finds this one, right? So all of this magic is happening behind the scenes. Now we're going to have the video about implicits very soon, where we're going to go through all the nitty-gritty details of implicits. But for now, the one thing that I want to mention is that this technique already works, also works for something that is already something that has area from the very beginning, right? So far we had some sort of circle and we converted it into something that has area, or we had a container of circle and we converted it into something that has an area. What I want to show you is that this technique also works with something that has been something that has an area from the very beginning. So we're going to have a val over here, and we're going to say, okay, this is a container of something that has area, and we're going to say, okay, so this is a container of something that has area, okay? And we're going to say, okay, so this is a container of, and we're going to create a something that has area, right? So before, as I said, we created a circle and we converted it into something. Over here, we're directly creating an instance of something that has area like this. We're going to use an abstract class, I'm sorry, an anonymous class, and it's just going to have an area, which is a double equals 1337, and we're using final override here, but you know, this is an anonymous instance, so it's final anyway. Okay, so if we have this container of something that has area, then we can still go over here, the same as we did over here, for example, right? We can go to the complicated algorithms, area twice, and we can pass in this container of something that has area. And now the only question remains is, how does this work? And in order to understand that, we need to desugar it first. So I'm going to duplicate the line, and what here is happening is we're gonna have this adapter, right? So this is the adapter that is happening, right? It's being called over here like this, okay, like that. I'm sorry, like that. And this has a second parameter list, right? So if I go, you know, I should create way more space, by the way, like this. This is way more important, okay? So this container or something that has area, it needs the second parameter, right? This convert that takes in a t and produces a something that has area. Now a t is a something that has area already. So the question is, what are we going to pass over here? So we sort of need an implicit identity function, right? So if we had an identity function like this, I'm going to go and define it over here, right? I'm going to call it def ID. It gets in some input, right? It comes in as a parameter over here, input, right? Input, and what it does, it also returns the input. Well, where is it going to get it from? Well, from the parameter, right? That's it, right? So basically what is happening, we can pass this ID over here now, right? And it's going to work, right? Because this is a function that takes something that has an area and converts it into something that has an area, right? But not doing anything. So essentially, if we have an implicit over here, then it should be passed in automatically like this. But we didn't have it before. So how did it work before, right? So how does it work without this? How does it work without this? And the answer is that this function already exists in the predef object, which is imported into every file. And this function is called conforms, I believe. We're not going to go into it and look at it. Just know that it exists. I just wanted to show you that this pattern also works for something that has been something that has an area from the very beginning and didn't need to be converted first. Now, because this functionality is so popular, I have shown you this in the previous few videos, that you know, and this is also why I called them all like this. So if we comment out this implicit def and simply mark this class as implicit, it will behave exactly the same, like this. And the same thing should happen with this implicit container. It actually might not work with this one, but let's see. Implicit, and this convert should also be implicit, like that. Let's see. Okay, it still works. All right, so we're saving even more syntax here. The next thing that we're going to do is I'm going to show you an even fancier syntax, and this is the one that will actually be deprecated in the upcoming versions, right? So this goes by the name of the ViewBound, which is sort of an even tighter blend between the parametric polymorphism and the ad hoc polymorphism, which is basically saying it is an even tighter blend between OO and FP. Okay, so what we're going to do is we're going to go over here and realize that we're basically requesting a T and a view from T to something that has area. And there is a thing where we can go to the parameter over here, right? And we can say, okay, we don't just want some T, we want a T that can be viewed as, right? So this is very similar to one of the bounds, okay? That can be viewed as something that has area. And if we have that, then we don't even need this parameter. Let's see. Now the only problem with that is now we don't have this name in scope. We don't have convert in scope, and I believe that this is what it is complaining about. It says, hey, where's convert? And this is where our ID function comes in, right? So if we take this ID, if I just bring it up a little bit, and I put it over here, right, like that, we don't need it to be implicit. I'm gonna remove the implicit keyword over here, right? But if we had, if we mark this parameter as implicit, right, then we could essentially use it to retrieve the convert function from the implicit scope, right? So we can say, okay, convert is this function here, convert, okay, and it comes from ID of something that has area. Okay, so we're basically saying, hey, give me that thing. I'm sorry, this is a function that takes a T and produces something that has area, right? So it's basically this type. So what is happening here is that we're saying, okay, compiler, please find this implicit the parameters in this implicit parameter list. Okay, and what is the parameter? Well, it's a function that takes a T and produces that something that has an area. Okay, well, do we have something like that? Well, maybe. And if we don't have something like that, then the code that is using this container or something that has area is just simply not going to compile, right? So this goes into implicit derivation again, right? So as I said, this already exists in the predef object. In fact, there are multiple of them. They're very similar. So I believe before I confused it a little bit. Well, actually no, I didn't confuse it. So there's one that looks like this over here, right? Sort of like this, right? And the other one that looks like that. So this one is called conforms in the predef, and this one is called implicitly, and the second one is the one that we need over here, right? So we need to say implicitly, right? So the purpose of it is just to get to get this name out, right? To get this object from the scope. So now if I remove that, it's going to behave exactly the same way as before. Now we're getting close to the actual proper encoding of the type classes, and you will see that the proper encoding of the type classes basically requires this, right? It requires this implicit parameter, right? So because both of these encodings, they require implicit parameters, this one is basically being frowned upon and is not used anymore. So this syntax will be deprecated soon, and now I'm going to show you the different encoding, the proper one, the one that you actually should remember. Another reason why it's being deprecated, by the way, because it encourages those implicits that's sort of happening like behind the scenes and you don't even see them. So they scare a bunch of beginners, and yeah, that's why it's being deprecated. Now the proper type class encoding is a bit more closer to the bridge pattern, in fact, than to the adapter pattern. The difference between the bridge and the adapter pattern is that the bridge pattern knows from the very beginning that it needs to be extensible in such a way, right? So it knows sort of about the bridges, right? So the bridges are basically the same thing as the adapters, but the algorithm knows about them ahead of time. And in the type class terminology, these are called type class instances. So instead of something that has an area, this trait over here, we're going to have a different one, which is going to be very similar, and I'm going to call it Typeclass Bridge for type T, right? So this is where we also see that this sort of notation is closer to objects, and this notation is closer to data structures, right? So now it's going to have an area of something that is a T and returns a double, and notice that it doesn't know anything about the T, right? Which is really cool. So now we're going to go to the complicated algorithms, and we're going to implement a different version of area twice. We're going to call it area twice 2 over here, and it will need a T, right? It will say, give me the T and give me that bridge, right? So it will say, hey, give me that bridge, give me that adapter, give me that instance, right? So it's going to be an implicit instance, similar to what we did over there, right? It's going to be instance of the type class bridge for type T, and it is a double, And over here, we're going to use the instance. Let me create some more space like that, right? So we're going to use that instance over here. We're going to call area on it. We're going to pass in the t, this one, okay? And then we're going to do the thing that the algorithm actually wanted to do. It wanted to calculate the area twice, like this, okay? So now it should compile, and now we're going to go and see how we can define the instances for them. So we're going to go back over here, and I'm going to go up to the shape adapter. Which is over here, and I'm gonna basically copy it because this instance for the type class is gonna look very much the same. So the only difference is that it's gonna smell a little bit less like object orientation. So it's not gonna be an implicit class, it's gonna be an implicit object, and it's not gonna be called shape adapter. It's gonna be called shape type class instance, right? And there is no parameter over here because this parameter is actually on the area, right? It's actually over here, right? So it extends not something that has area, it extends the type class bridge for type shape ds. Okay, so this is the shape type class instance. I'm gonna call it 4ds. Okay, extends type class bridge for type shape ds, overrides the area where the shape is shape ds over here. So this is basically our t. I'm gonna call it t. Okay. Now the implementation, looks the same over here, right? We can let's call it shape whatever, right? So that it looks very similar. Okay, like this. Right, so now we can go down and use this instance, right? So basically the same way over here as we use this one adapter. I'm gonna duplicate this line over here. So the first syntax is gonna look like this. So we're passing in the circle, and we're passing it the how did I call it? Instance something shape type class instance 4ds. It's actually mentions. Let's just call it like the shape type class instance, okay? Because it's for shapes, okay? So we're passing it like this, or we don't pass it at all. I just need to put in a 2 over here, right? So it's very similar, right? So this and this is very similar to this and that. Now the other cool thing that I'm going to show you is that if I comment out this line, right, and I comment out the instance, which is over here, right, then we can actually go to the original algorithm, right? This is the original algorithm. This is how it looked like. Look how little code is required to convert it to an actual instance. We just need to say implicit over here. I'm sorry, this is the GeoEntities thing. I wanted to go to the other one. Here, we just need to say implicit over here, right? And we need to say extends, where is it? Typeclass bridge for type shape ds, like this, right? And it still works. So basically it has been an instance of the type class all along. Even in the video that I made like a year ago, it already has been an instance of this type class. It's just that only now we're actually learning about it properly. Okay, so I'm gonna revert that. In fact, it doesn't really matter if I revert that or not, but let's just do that. Enable this one again, like this, compose again, there we go. Okay, so the instance for the container type class is gonna look very similar to this one, but I think it's faster if I'm just gonna type it out. So it's an implicit class container type class instance of t, which requires an implicit instance for the type class bridge for type t, which extends a type class bridge for container of t, right? And it's going to have the body, and in the body it's going to have final override def area, which is going to take the container, which is a container of t. Okay, it's going to produce a double, so it's going to call instance dot area, and it's going to pass in the container dot element, and it shouldn't compile, I believe, because there's a limitation for the implicit classes. Yeah, it says implicit class must accept exactly one primary constructor parameter, and right now it accepts basically 0. So to avoid this limitation, we have to create the implicit def similar to what we have been doing before. So this is container type class instance for t, and now that one gets an why did it do that? I wanted to do that. Okay, so this gets in the implicit instance for type class bridge for type t. Okay, it produces the typeclass bridge for type container of T, and all it does, it creates new container typeclass instance of this instance, and now we can remove this implicit over here, and we can also remove this implicit over here, like that. So now we can go to the usage. So this was the original usage. In fact, I can do that as well. Okay, and now I'm just gonna type it under. So we're gonna go complicated algorithms dot area twice of some container of circle, and we can pass in the instance container type class instance, or we can do without the instance where the compiler is going to resolve both implicits for us. Okay, I just forgot to do the 2 here like that. There we go. Come on, there we go. Now, similar to the view bounds, we also have a fancy syntax for type classes, and it goes by the name of context bounds, right? So instead of having this implicit parameter over here, right, we can say, like before we said this, but now we're going to use a colon, right? We can say colon, and it's just going to be a type class bridge for type, like this. Okay, so now we don't have this parameter over here, right? And we want to use this parameter though over here, so we don't have this instance. And similarly to before, we need to request implicitly the instance of the type class bridge for type T. And in fact, in this case, we actually can remove that because the compiler is going to be smart enough to infer that that instance for that type for us. And now that we know the syntax, we can actually go back to our original algorithm and say the same thing. We can say over here, so this is the area twice 2, not for some T, but for some T that is in the constants of the type class bridge, right? And now we don't need to have this instance over here like that, right? So now it looks more civilized, so to say, and all we need to do is we need to request that instance over here. So what we do is we say implicitly, okay, we need a type class bridge for type T, like this. Okay, it should be fine. Yeah, it's fine. Now I'm not going to show you this, but if we had like multiple parameters in that second parameter list, in the implicit parameter list, then you could also use the syntactic sugar over here, right? So you could say over here, and also some other type class, and so on and so on and so on. In fact, this is a very typical pattern in functional programming in Scala. Also, there is sort of a convention to define a companion object for your type classes like this. So I'm going to have an object type class bridge for type over here, and it will have basically implicitly defined. It will be called applied, right? But it's doing exactly the same thing as the implicitly thing is doing, right? So it's going to say, okay, so give me the instance of the type class for type T, and I will just produce it to you, right? So this looks very much like the identity function, so it looks very similar to the implicitly function. In fact, this is the implicitly function, okay? And all it does, it returns this instance. So now that we have this thing, so it's sort of the convention. So instead of using the implicitly function over here like this, I'm going to duplicate that. We're just going to say, okay, give me the instance for that T over here. I did some mistake. T is not there. Oh yeah, I should have removed that, obviously. All right, so yeah, so now it works. Yeah, so this is sort of a convention. So instead of using the implicitly function, have a companion object with the apply function there, and it basically over here says, okay, I need an instance, and this is how you get the instance. A few last things that I'm going to show you is, first of all, if you don't have an instance for something, let's say we don't have an instance for this one, right? This one. Then we're obviously getting a bunch of error messages produced, right? But basically it says, could not find implicit value for evidence parameter of type class bridge for type. First of all, it's called evidence because basically the compiler is providing an evidence that this type can be passed in because it found this adapter, it found this instance. So what I can show you is that there is an annotation that allows you to change this compiler message. So instead of could not find implicit value for evidence parameter of type blah blah blah, what you can do is you can go to your type class instance over here, and you can add an annotation. You can say Scala annotation over here, and it's called implicit not found. Okay, and you can say over here, give me an instance of Typeclass bridge for type, and you can have for, and you can use dollar, and you can say T over here. I'm sorry, it was the curly braces like this, and this will be used as the error message. So if I scroll down, now it says, give me an instance of Typeclass bridge for type for main DS container shape DS. Okay, so you can use this not just to change some English over there, right? This is usually used for explaining how to find some instances, right? So you might have some default instances hidden somewhere, and you can explain how to find them. And the common example would be the Scala concurrent future that I'm going to show you in a second. Hold on, where is that thing that I commented out over here? Okay, and I commented back in. Okay. A bunch of errors. What? Why? What's happening? Conflicted message shape. Oh, did I uncomment the wrong one? Hold up. Where's the one? Here, this one. This one, there we go. Okay, everything is green. So I'm just gonna go over here. I'm gonna create a tiny main method over here. So I'm gonna create a method called app extends main over here. Let's switch to running that main. Let's do run app. Okay, it says that there is no oh yeah, I put it in the library. In fact, we already have so many mains. Oh, okay, whatever. I'm gonna just put it over here. Okay, like this. Okay, so now I should at least find it. No main class detected. What? Why? Oh, we're in type classes, so let's go to app and do the same thing to run main app. Oh my god, I'm falling asleep. Object main extends app. That's what I wanted. This video is way too long. All right, so if we try to create a concurrent future of print line hello world, it doesn't say that it didn't find an implicit instance for some type class. It says cannot find an implicit execution context. You might pass an implicit execution context parameter to your method or import Scala concurrent execution context implicit global. Let's actually try that. So let's import that one. I'm gonna copy that. Okay, I'm gonna go and import it over here. Imported, right? So it's already implicit, so the compiler will find it. What? Class not found. Oh, I renamed it to main. Oh, Jesus. Okay. I should not record videos that are so long. All right. So if we go down over here, now it's going to say, hey, now I found this instance, and you can also use it explicitly because this is essentially just a second parameter list over here, right? There we go. All right, now guys, this video has been super long, but trust me, we barely scratched the surface of type classes, and there are so many details that surround the topic, and in fact there are even more details that surround the topic of implicits alone. So please don't fall in love with type classes before you see my upcoming videos about implicits and well, even more about type classes. For now, simply remember that type classes are a mechanism for adding behavior to your data structures, or in fact to objects, because remember somewhere in the middle of the video I said that we're only going to go for the data structures, but for the objects it will look exactly the same. The adapters will look exactly the same line by line. Okay, so again, remember, type classes are a mechanism for adding behavior to existing data structures that may or may not be yours, and they are mostly useful in static type languages. And the last thing is that remember that the type class itself in Scala is a trait, and the instances extend this trait. So we're sort of using subtype polymorphism to implement type classes. Remember, because subtype polymorphism and type classes are both kinds of an ad hoc polymorphism, but at least in Scala we're using one to implement the other. Whereas in a language like Haskell, where type classes come from, it's built into the language, and in fact over there they actually use the word, the keyword class to define type classes. Okay, and in Scala we can't do that because we already have the keyword class for the object-oriented version of class, right, which is a blueprint for the objects that are being created. And this confuses a lot of beginners because they hear type classes, oh, that must relate somehow to the object-oriented classes, but it's not. All right, this is all I got for you today. This video got way too long. I am sorry, but please, if you liked it, don't forget to click the actual like button, subscribe if you want to improve the developer inside you, and most importantly, take care.